Hi, this is Alfozia Nihar from At Home Tuition. Welcome to our session today. The topic that we are going to discuss in our today's video is area between the curves. Under the topic applications of integration, this is one of the important concepts. The topic area between the curves. This helps us to learn about the area between the graphs of two different functions, that is equal to the integration of a function f of x minus the integral of the other function g of x. F of x and g of x are two different functions. This is how we write the integration of area between the two curves f of x and g of x. A denotes the area between the curves. Here in this video we are going to learn about evaluating the area between two different functions using a difference of definite integrals. First, let us see what is the area. Area is nothing but a quantity that expresses the extent of a two-dimensional surface, or it can be a shape, or it can also be a planar lamina in the plane. Area between the graphs of two different functions is equal to the integration of one function f of x minus the integration of other function g of x, where f of x is greater than y of x value, or y value, you can say that. The area between a positive valued curve and the horizontal axis. It can be measured between two values a and b, the leftmost x value and rightmost x value. And b is always greater than a on the horizontal axis, and it is given by this formula. A to b, it can be of any function. Okay, please have a glance over this figure, a graph with two curves, and we are supposed to find the area between these two curves. Area can be understood as the amount of material with a given thickness that would be necessary to fashion a model of the shape, or the amount of paint necessary to cover the surface with a single coat. It is a two-dimensional analog of the length of the curve. One-dimensional concept, that is. Or you can also discuss the, you can also learn about the volume of the solid, a three-dimensional concept. Okay, the area between a positive valued curve and the horizontal axis measured between two values a and b. B is defined as the larger of the two values on the horizontal axis. It is given by the integral from a to b of the function that represents the curve. The area between the curves, the graphs of two functions, is equal to the integration of f of x minus g of x dx. Let us start with an example. Here is the first example. We are supposed to find the area between the two curves x and 0.5 x square, and it has the interval. So this function is over the interval from x is equal to 0 to x is equal to 2. There are two curves actually, y is equal to x and y is equal to 0.5 x square. They both meet at the points. I'll show you. If you draw the graph, you can understand that these two graphs meet at 2 points. The first point is 0, 0 and the second point is 2, 2. And you should know that this graph x is greater than half of x square over the interval 0 to 2. Now the area can be calculated as that. I'm going to write in the way. A equal to, the area is equal to integral over 0 to 2 x, the first graph, minus the second graph, 0.5 x square dx. So instead 0.5, let me write it as 1 over 2. Now let's split the integral. Now by applying, I'll get 1 over 2 x square here, and for this one 1 over 6 x cube, because 3 in the denominator. 3 times 2 is 6. First plug in 2 and then subtract and plug in 0. So I'm getting, by simplification, I'm getting 2 over 3. This is the area for the two curves x and 0.5 x square. Hope you got this concept. So far we saw an example for the upper and lower graph. Now let me take the second case, right and left graph. The second case is almost identical to the first case. Here we are going to determine the area between x is equal to f of y and x is equal to g of y on the interval c, d, with f of y is greater than or equal to g of y. So in this case the area will be f of y minus g of y. So integration over c to d, both the formulas, the area for up and right curve up and down curve, and for this left and right are perfectly serviceable formulas. However, it is sometimes easy to forget that these always require the first function to be larger of the two functions. So instead of these formulas, we will instead use the following word formulas to make sure that we remember that the area is always larger function minus the smaller function. For the first case, we can use this formula. And for the second case, left and right curve, you can use this formula. Using these formulas will always force us to think about what is going on with each problem and to make sure that we have got the correct order of functions when we go to use the formula. Let us discuss one more example detailedly. Here is the next example. We are supposed to determine the area of the region enclosed by two curves, y equal to x square and y is equal to square root of ax. Let me draw the graph first. Here is the graph. First of all, just what do we mean by the area enclosed by? This means that the region we are interested in must have one of the two curves on every boundary of the region. So, this graph of two functions with the enclosed region is shaded. Also, please note that we don't take any part of the region to the right of the intersection point of these two graphs. In this region, there is no boundary on the right side. Am I right? And so, it is not a part of the enclosed area. Remember that one of the given functions must be on the each boundary of the enclosed region. Also, from this graph, it's clear that the upper function will be dependent on the range of x that we are going to use. Because of this, we should always sketch a graph of the region. Without a sketch, it is often easy to mistake which of the two functions is the larger one. So, in this case, most would probably say that y equal to x square is the upper function, and they would be right for the vast majority of the x. However, in this case, it is the lower of the two functions. The limits of the integration for this will be the intersection points of the two curves. So that's why I enforced that we should sketch the graph before proceeding. So in this case, it is pretty easy to see that they both will intersect at x is equal to 0 and x is equal to 1. So these are the limits of the integration. If the limits are not given, you better draw the graph and find the points, the limits of the integration. So the integral that we will need to compute here is to find the area between upper and lower function, right? So we are going to use that formula only. The points are 0 and 1. Larger among the two is square root of x. Now you can take the integral. So square root of 1 over 2, that will be x raised to 3 over 2 divided by, okay, so 2x raised to 3 over 2 over 3, and for this one x cube over 3. Now apply the limit 0 and 1, we will get 1 over 3. Hope you are clear with this example? Okay. Before moving on to the next example, there are a couple of important things that we have to notice. First, in almost all of these problems, a graph is pretty much required. Often the bounding region, which will give the limits of integration, is difficult to determine without a graph. Hope you understood this. Also, it can often be difficult to determine which of the functions is the upper function and which of the lower function without any graph, no? So this is especially true in cases like the example that we just discussed, where the answer to that question is actually dependent upon the range of x that we were using. Finally, unlike the area under a curve that we looked at the previous topic, and the area between the two curves will always be positive. In case if we get a negative number or 0, we can be sure that we have made a mistake somewhere, and we will need to go back and find that. So notice as well that sometimes instead of saying region enclosed by, we will also say region bounded by. Both are the same thing, they mean the same thing. Hope you're clear so far? So far we were discussing the examples with only one term. What will you do if you have so many terms like a polynomial, something? So we have to be careful with the parenthesis, because in this parenthesis we will be plugging in one expression and another expression. So you can better write parenthesis, two different parentheses for this one. So you have to be careful with the negative sign. One of the more common mistakes students make with these problems is to neglect the parenthesis on the second term. So while distributing the terms in the second parenthesis, be careful with the negative sign, because once you multiply all the terms with negative sign, the signs actually changes. Hope you got this point. We can discuss more examples under the same topic in our next video. So, area under the curve. This integration is nothing but integration can be thought as measuring the area under the curve defined by f of x between 2 points. Here we are taking A and B, upper and lower point. In case if you get any query, kindly let me know. See you in the next video. Have a great time.